I'm Kevin Keating of Telecom Real Estate Services, and welcome to our new block data center design. We've designed our building with 200 watts a square foot of critical load on the floor. This requires a large central cooling plant. So we've designed chillers with traditional cooling towers. The next challenge is how do you distribute all this cooling? So you could do a traditional approach with cracks on the floor, but that really impacts the efficiency of the space. The next alternative is air handlers on the roof with air side economization. This is a great system and very traditional. We looked at the next evolution of the air handler system and thought it was a very interesting way to go. It's called a hybrid cooling system. Same basic footprint on the roof, but this combined unit has DX cooling, indirect evap, direct evap, and air side economization. With this system, you can eliminate the chilled water plant and install the system in modules. So we videotaped an actual installation and have all the specs online. So take a look. This rendering of the building shows the 12 roof-mounted air handler units, either the new hybrid units or traditional air handlers with air side economization. The area allocation plan shows the chilled water plant in the upper left of the building, with the cooling towers being proximate. Also to the north of the building, you see the makeup water towers.
This end of the unit, this is the new Energy Labs hybrid data center unit. The bulk of the work is done by the indirect evap cooling section, or IDEC section. This is the IDEC pump. All we're doing with this section is making cold water with this evaporative media, taking the water out of that sump and pumping it down through a piping loop to a water cooling coil on the supply side of the air duct tunnel. And that lowers the temperature, effectively doing the bulk of the cooling for this size unit.
And what is this unit?
This media here?
Yes.
This is cooling tower media. It's different from the Munters media on our direct evap section in that its whole purpose is not to make cold air, its whole purpose is to make cold water. So it's the most efficient media that we can buy to make cold water. So it's just typical cooling tower media, nothing special. That is the outgoing side, the front side of the IDEC section. This is the IDEC media. When this is in operation, you'll have water streaming down over it. These fans will be on. These are the exhaust fans. Those fans will be on when we're in either economizer mode or IDEC mode. These fans will be on, pushing air across this section, making cold water. Basically, all this does is make cold water. We then take that water and pump it down into the coil in the supply side section for indirect evap cooling. These fans are what we call a quad fan arrangement. There's 4 fans, any 3 of which are required to do the duty. The 4th is redundant. We do operate them all on a common VFD, so that if any one fan fails, we get a signal, we ramp up the VFD, and it controls the other 3 fans to the static pressure that our set point is in the space. So we do have some redundancy on a unit level beyond N+1. So, and that's about it for this section. This is really the brains of the operation right here. This is our custom mixing box. This took a lot of development to come up with this strategy. We bring return air up in the middle of the mixing box, and then we have this V-bank of dampers arranged so that we can either bring return air through the exhaust side of the unit, or we can bring return air through the supply side of the unit on the other side of this block of dampers. We also have the ability to bring in outside air for the exhaust for scavenger air makeup for the IDEC section, or we can take that same outside air into the supply air stream for economizer use. So we have a lot of flexibility here in how we can mix air to achieve our set point with the minimum amount of energy used and the minimum amount of other components needed. So this really here, 7,000 plus hours a year, is all that's going to be working. These dampers will be modulating with the fans, supply and exhaust fans. These dampers modulating to meet the set point of the supply airstream. That's, like I said, 7,000 hours a year. All you're doing is using fan energy to achieve your set point. Very energy efficient. It's all done with sensors, so that we're not doing any math or crazy equations. It's all done with sensors, and it's all automated through the ALC package control system that comes with the unit. Okay, the quad fan arrangement you see here, we took a look at the other side of the fans with the motors. This is the front side, the inlet side of the fans. They're all equipped with backdraft dampers here, so that in the event of a failure of any one fan, the backdraft damper stays closed and it does not allow air to short circuit. In the event of a fan failure, the other three fans will ramp up via the VFD and do the duty of the full unit without the fourth fan running. So the fans are selected to operate any three of the fans can do the full duty of the unit in the event of a failure of the fan, and we don't waste energy by short-circuiting air by having these backdraft dampers in place. So. This is the supply side of the airstream where we're actually taking air, either return air or outside air from the mixing box section and bringing it into the data center. So we actually now care about the quality of air here. We're going to be filtering it. We have a pre-filter, 2-inch pre-filter, and a 12-inch final filter. We can put whatever level of filters, 65s, 85s, 95s, whatever you want in here, depending on the conditions around your space, your site. And we filter the air, and we bring it into our supply air fan bank the same way our return air, exhaust air fan bank has backdraft dampers on each fan. So in case we lose one of these fans, in this case we have 3 supply fans, any 2 of which are required to do the full duty of the unit. The third one, if we lose any one of these, we can ramp up the other 2 fans to do the 100% duty of the unit. So this is the supply air section now. The air is moving the other direction down towards the supply ducts into the data center. So that's where we're headed right now. Issue with backdraft. Okay, this is the supply fan section. We're now taking air, passing across those filters into the inlets of the fans, and these are our 3 supply fans. These are airfoil plenum fans, very efficient energy-wise, and what they do is pressurize this space in front of this IDEC coil. This is the IDEC water coil. So the fans will bring air in, pressurize this whole space, and then because this coil takes up the whole wall here, there's an even airflow across this coil that then takes that cold water through it. You can see the supply and return lines out here on the end of the coil. It takes that cold water from the IDEC sump on the other end of the unit through this coil and drops the air temperature, whether it's return air or outside air. It drops the temperature of that air and then returns warmer water back to that sump. So this is basically your IDEC coil, and the reason it's called IDEC, indirect evap cooling, is because there's no direct contact with the water and the airstream. So it's the 2 bundles in here are all encapsulated copper tubing. The fins do the heat transfer, aluminum fins, and the entire system is not, the water system is not exposed to the supply air stream, so that's why it's called indirect evap cooling. This system will do the bulk of the load of the cooling for the data center when we're beyond economizer mode. So as soon as we go into the first stage of cooling, we're going to either be doing, depending on enthalpy, we're going to be doing indirect evap cooling or direct evap cooling, which you're going to see in a minute downstream.
DX cooling is also provided the hybrid unit. This is the external condenser unit, and at the left you see the internal media for DX cooling.
Now we're in the supply side direct evap cooling section, which is at the end of the unit, which is also the supply into the data center. I'm standing on a grating here that is actually the supply opening, ducted down into the data center. Because of the plenum fans, we have a nice even airflow profile here, so we have a nice sized supply air opening here. This is the direct evap section with the direct evap media by Munters. The idea with this media, as opposed to the IDAC media, this is direct evap. The indirect evap on the other end has cooling tower media. Because all we're doing with that is making cold water. This, we're actually making cold air, and we're also humidifying the air with this direct evap. We have three stages of vertically separated media. Each one has a separate pump from the common sump here, and the common sump then pumps water up and dribbles it down over this media. The air flowing across the media then is cooled down, evaporative cooling, just like a swamp cooler basically, 2,000-year-old technology. The water in this section is coming in direct contact with the air, so it does pick up humidity as well as cooling. So we can only use this section, this media is turned on and effectively doing evaporative cooling if the enthalpy of the room says it's okay to do that. And because of ASHRAE TC 9.9, we now can go from 20 to 80% relative humidity in the room, which gives us a lot more flexibility to use this type of system. So we're taking full advantage of this cooling and humidification capability in this final section of the air handler. So this again is direct evap, so we must use city water in here. The indirect evap section on the other end, we can use city water or industrial reclaimed water, which is cheaper. So it's not in the airstream, so we can use it down the other end, but we have to use city water for water quality issues for health reasons in the supply side airstream, which is on the direct evap section. Again, we have TDS monitors for the sump, so that as the dissolved solids build up, we can flush that out at a certain prescribed set point. We also have high and low water level limits that are alarmed to the BMS, so that we actually can monitor the condition of that sump, both from a water quality standpoint and a water level standpoint as well. So very integrated control system. It's actually a very simple unit. If you think about everything that's in here, there's really nothing new in terms of technology. What's really new is how we've packaged it and arranged it for a data center application.